Archimedean, let's see, so 2, 4, 3. Archimedean property. And according to Bartle and Sherbert, it means that this is what it stands for, the set of natural numbers, is not bounded in so that's the name of the property. Statement of the property goes, if x is an R, so let's make that, okay, yeah, we can do red. If x is an R, so here's our x. If x is an R, then there exists then, oh, then there exists, yeah, that's correct. There exists n dependent on x and this number, whatever it is, belongs to set of natural numbers such that x is less than or equal to nx. For, oh no, and it stops right there. So this means the n has a relationship with x. Okay, so let's kind of like do this here. So n x okay, so x is real and n is natural number, and the natural number depends on x, or n it has a relation to x. For its value, whatever the value n is going to have, it depends on x. So
is that what such that x, is that the relationship there?
that is the relationship. In other words, give me an x and I will find you to the right of x a natural number that is bigger than the real number. On the real number line, find me any real number x on the number line. To the right of it will exist a natural number n.
You could break the equals to part of this.
Yes. And do they do it with, yeah, they do it with contradiction. So again, you're on the zone. Let's see, statement. If x belongs to R, so let's do that. Let's just make a picture. If x belongs to R, here's our real number line. if X is here, if X is here, if X is here, let's just go crazy here. Still work.
Yep.
Okay, so give me an X, and I'm going to tell you that there is an N, a natural number, to this X's right.
Yep.
Give me an X, and I'm going to, there exists, this theorem says, this Archimedean property, that there is an N to the right of it.
Most definitely.
Give me an N. Yes, sir.
Nope, you can't do that,
Why not?
because then it's less than the other negative X.
Oh, I'm just, every real number to the right of it is going to have an.
Yeah, but not right there. It can't, the N.
Oh, you're right.
X cannot be to the left. of the
Oh,
negative X.
yeah. Yeah, that does suck. Okay, so you're right. So it has to be positive real numbers.
Mhm.
Um,
Well, it can be negative real numbers, but N just has to be greater than 0.
No, but then it doesn't work. N is on the number line. So this N only helps us if the real numbers are positive. So very good, very good. All right. So that's excellent. So this won't work, and this is good. We'll keep this on our. So we're going to take this off. So for instance, let's just pretend this was 27, this was 30, this was 120, and this one was 122 on the number line.
So
Real number. Okay, you just saved the day. You're in the zone. That means there's a Archimedean property will work for, it is not bounded, and where you see the set of natural numbers show up only where the real numbers are positive too.
yep.
They don't sit to the left of the 0.
What you could draw to demonstrate it is like both number lines where the number line of real numbers extends past 0,
Yeah.
and the number line of natural numbers like just stops there. Like,
Yeah.
This is,
Well, this is the
oh yeah.
yeah, that's
There
it.
you go. Thing.
Okay, all right. So let's delete this and let's do the proof. So in Bartle and Sherbert, they use this a lot. This is a common usage that we don't see in Belding and Mitchell. So, okay, so proof is by contradiction. Proof if the assertion, meaning this Archimedean property, this assertion is false, then N for all N in set of natural numbers. So what this is saying is that there is an X, an upper bound, basically.
Oh, we turned it around.
Yeah, so we turn it around. So if you go here and you got an X here, you got an X here, you got an X here, and everything is working quite fine. You have a real number, you got an N X. You got a real number, you got another N to the right. you got a real number x, you got another n, but this x, after this x, there is no n here. No n, none, oh, no n anymore. So that is the opposite of what the theorem is saying. Yes.
So the set of natural numbers is not bounded in R. Why does that only pertain to the upper bound? Because there is the lower bound of 1.
We know that already.
Okay.
Yeah.
So that's just assumed.
No, it's this. The reason why the upper bound is more important is for things like this. If you have an n, and n is not bounded, doesn't have an upper bound, you can do +1.
Oh.
So you can go from here to the right, and you can do induction proofs.
And that's the nature of natural numbers, is the +1 all the way.
Yeah. To the left, let's say you're on 1, and you want to go left, you're going to hit 0, which is not in the natural number.
And you can't go left, right?
Yeah. So usually we go to the right to prove that this is true for all numbers starting here going all the way to the. So this thing comes out of the fact that there is no upper bound. So, and since this looks like the definition of upper bound. So this is all n, and then this is our upper bound. Since it looks like a definition of upper bound, we can say therefore x is an upper bound for the set. Delete this. For the upper bound of they're doing n, which is exactly the opposite of the statement of the theorem, right?
The statement of this theorem is there's no upper bound n.
No upper bound x.
No upper bound. There's no upper bound within n.
N is always bigger than any possible upper bound. That's what this statement says. And here we are saying x is an upper bound of n.
So in this proof, x is any upper bound we can come up with, and the n is the other guy saying, nope, I found another number, found an n+1.
This is saying, oh yeah, this is saying no, there is an n+1. And also another thing about natural numbers, they go 1, 1, 1. Easy to manage them too. Okay, all right. So therefore, what is the we get our favorite? Let's draw the picture here before we forget. So for this line of the proof, the picture goes. Put the picture here. We have a x. Now we have a x. And we have a n here. So I probably don't need to put a curly round bracket, but I just did that.
Yep.
Because both numbers are actually on that line. The red n and x are both on that number line. Therefore, by here, oh, you need that.
Yeah.
Therefore, by the completeness theorem, completeness property we can say the non-empty set N has a supremum. Another name for supremum is LUB. And we're going to call that LUB in this book. They like to call these things U. U, supremum U, LUBU of N. So the set N has an upper bound X. If it has an upper bound X, completeness property says if the set is non-empty and has an upper bound.
It's got a least upper bound.
Yeah. And therefore from this, because it's non-empty and has X as an upper bound, so this is an upper bound. Okay, so next we have, now we're just gonna mess around, and because this is by contradiction, let's mess with this thing. So therefore by the completeness property, non-empty set N has a supremum or least upper bound U. So U has to be smaller than this, otherwise it won't be the least upper bound. So we put U right here.
So are we teeing up our contradiction right now?
We are going towards it's going to hit us very soon. And it's a very beautiful contradiction. So if we have U, and this is our LUB. Now we're going to, so now what we do is this is what we're going to mess around with this situation and create a absurd situation. So subtracting one from U gives us U minus 1 U minus 1, which is smaller than the supremum, as in LUB of N. So I subtract 1 from U, pull this guy here, and we get right here U minus 1. U minus 1 is just a number on the real number line. So we got N, the natural number. We got a real number, U minus 1. We got a second real number, U, which is the LUB of the set of natural numbers. And then we have an upper bound for N. We got 3 real numbers and 1 natural number on the real number line. All right, next. We can then, what we do is we simply say, therefore, so the question is, what kind of a thing is this, right? It is not an upper bound of N because Uh-huh. Okay, so so it's kind of like as you're doing this, you're smiling about the whole thing. So it's kind of like, all of this is wrong. This whole picture is wrong because it's based on
Everything we've done up to here has been wrong.
yeah, it's like messed up. But we still try to do right things in the wrong.
Yeah, well, 2 wrongs don't make a right, so we'll keep that.
But 3 wrongs do make a right.
Really?
No, well. All right, so we have, since this is not an upper bound of n, because if you have an upper bound, there cannot be any m here, right? Because that's an upper bound. That means all the numbers in set of natural numbers have to be smaller than this upper bound.
That stops them in their tracks.
Yeah, so m cannot sit there. M cannot sit here because this is the least upper bound. All the elements in the set of natural numbers n has to be smaller than this. If there is going to be an m, because this is not an upper bound, this is just a real number, there can be an m right here.
Yep.
This fits in because it's to the left of LUB and to the left of the upper bound. So we can still have a m, as in, this is just another m, basically, right?
Yeah.
Okay, so we can have another natural number. We can have natural numbers all the way, but after the LUB, there's no chance because they just stop.
Yeah.
Because this is the least upper bound.
They just
This,
go beyond.
yeah, this is the boundary, right? This is the boundary wall. It's like, yeah. Okay, so.
Well, the
Yes.
way that I'm imagining this whole situation.
And there's one more. Okay, therefore, because this cannot be an upper, it cannot be a upper bound.
U minus 1 can't be an upper bound?
This cannot be an upper bound of n because this is the upper bound. This is the least upper bound and this is the upper bound officially. When we subtract 1 from the least upper bound, what we get is just a real number on the real number line, and it is not an upper bound for n because that's the upper bound that we just established. Once you establish your LUB, you can't just mess around with it, kind of.
No, that's your lambda, that's your baby.
Yeah, that's your baby that holds the whole family together.
That's the glue right there. You
Yeah.
hold on to that.
So therefore,
Child.
u minus 1 is not. So subtracting 1 from u gives us u minus 1, which is smaller than the supremium LUB of n, which makes it not an upper bound, not a least upper bound, but smaller than both of those upper bounds, is not an upper bound. And because it is not an upper bound of n, if u minus 1 was an upper bound of n, then there couldn't be any natural numbers to the right of u minus 1, right? That's what this is saying.
Yep.
This says, therefore, u minus 1 is not an upper bound of n. If u minus 1 was an upper bound of n, then it couldn't have to its right natural numbers. But because it isn't, it is not, therefore, so there exists m, and we could have just used the letter n again, but it would have been confusing. M that is in the set of natural numbers n with, and what's the relationship over there? U minus 1 is less than M. Because between two real numbers are infinitely many. So there is going to exist infinite real numbers, and some of them are natural numbers. Okay, so, and for that infinitely many thing, the infinitely,
So there's infinitely many real numbers and infinitely few natural numbers.
yes,
within it,
between these two, yeah.
which means
Infinitely many, yeah, very good. Natural, you're in the zone, man. And real. That's right. Infinitely many natural and real numbers between u minus 1 and u.
Oh, shit, I see what we just did. Wow. So we just said that upper bound can just keep on chugging. Like we choose another M, it'll push it up.
No, it won't. No. This we've already decided that x is the upper bound after which there is no natural number. Because there was an upper bound and the set of natural numbers was non-empty, therefore there was an LUBU. All we're saying here is that between two real numbers, there are infinitely many natural and real numbers. Therefore, we will find a natural number M. That's
Break it. What if U is 2 and U minus 1 is 1? There's no natural numbers between 2 and 1.
Yeah, 2 and 1 will be only reals. Yep.
So there's not well, I guess, no, there can't be infinitely many. There can at most be one natural number between them. Because it's minus 1.
Oh yeah, that's true. That's true. So I'm going to take that off. You are not in the zone. There are infinitely, okay, there's going to be finitely few and infinitely many are real numbers. And finitely few as in 1.
I thought you were talking about the whole number line. Like
yeah, no. Oh, that's why you were agreeing with me. But you found out that it's better not to agree sometimes.
It is better not to agree.
Okay, let's keep going. Very good. That's a good save. Minus 1 means that this is a fake M. There is no M.
I mean, there could be an M if used 1.5 and
one and a half. Half is not a natural number.
No, but those are real. U and U minus 1 are both real numbers. You could have 1 and 1.5 and 1/2, and in between them 1 exists.
See, you were right. If this is 1, this is U plus 1. There's nothing here. There is no M. That's why it doesn't work. M is fake.
But M could be real. M
No.
is fake sometimes.
No, it's fake right now. You were right. Stick with your intuition.
Well, my intuition keeps going.
No. Stay in the zone. Put an upper bound on your intuition.
Sound like Epicurus.
Yes, sir. Whoa. Okay, sorry. Internet. Okay, let's keep going. But I think we saw a lot today. We saw a lot over there.
I still see something, but you're not buying it.
No. Okay.
I think you're going to see that M is real.
Adding, you'll find out just right now, you're going to find out M is not real. Adding, you're going to find out that M was a joke on us. Adding 1
Adding 1
gives. Let me put it in red. Adding 1 gives it gives us, so let's add 1 to this thing, u minus 1. So I'm adding, sorry, fake. So I'm adding 1 to the left-hand side and adding, sorry, I'm adding 1 to the left-hand side and adding 1 to the right-hand side. This gets cancelled and we get, ta-da! And what is this saying?
Says that my intuition was correct.
This is saying that m plus 1, that to the right of our least upper bound, the set continues,
Which is not true.
which is not true given our reverse
Yep.
assumption. Therefore, this situation is actually true because u is a real number, but because we had put our restraint, so this is a contradiction. We have so
reached their contradiction here by
our assumption is that there are no natural numbers to the right of u, and we get that. So in our, this is a contradiction. Let me write that. This is a contradiction. This contradicts our contrary to the theorem assumption that there are no natural numbers to the right of a LUB or right of LUB U. Okay.
what I was